Okay, welcome to Chapter 8. This is the second in our look at using samples to make claims about populations. So the obvious question might be, if I've got a sample statistic, like a sample mean or a sample population proportion, how accurately does that represent the population parameter? So coming at that question directly, you might say, well, it isn't accurate. The population parameter is almost certain to be something different. But we know from what we were doing earlier in Chapter 7 that we can make claims about populations using samples. So the question then becomes, how big would an interval have to be around the sample statistic to have a good chance of capturing the true population parameter? And that idea of confidence intervals is the theme of Chapter 8. So first off, some new words. When you take a sample and you have a sample statistic, you could call that a point estimator of the population parameter. You could say that it estimates the population parameter. But of course, the question then becomes, how accurate is it? And that might be based on how big the sample size is. Really, you're asking the question, how likely is that to be right? A confidence interval is made out of two things. So there's the point estimate. So in our notation, that's theta hat. Theta hat is a theta with a hat on it. That's the point estimate. Now, remember that a point estimate is just your sample statistic. So when we talk about a point estimate, we're saying that that is the sample mean or the sample population proportion. There's also the thing that makes it into an interval, and that is the margin of error. The margin of error is denoted with an E, and so what we do is, to make the interval, we add and subtract E. So here's our interval, the point estimate plus or minus that margin of error. Of course, plus taking you to the right of the point estimate, minus taking you to the left, making an interval. The level of confidence is constructed out of our alpha, our level of significance. The level of confidence is 1 minus alpha. If someone tells you a confidence interval, you might ask yourself, well, what does that mean? For example, suppose that someone told you that you have a 95% confidence interval of 0.65 less than p less than 0.73. So then what we'd say is there's a 95% chance or probability. I'm just going to say probability at this point, but later on we're going to just start saying chance, that the interval 0.65 to 0.73 contains the population parameter, or the population proportion. Now, we can say this a little bit more directly. We can emphasize the fact that we don't yet know the true population proportion. We've got a sample. So we can say that that interval captures the true population proportion 95% of the time. So here's another example. State as an interval and as a sentence. We've got x bar equals 25. So here we're talking about a sample mean. The margin of error is 8, and alpha is 1%. So the first thing that we're asked to do is state as an interval. So as an interval, we'd probably state that exactly the way you'd expect. We'd take that 25 and add and subtract 8. So 25 minus 8 gives us our lower bound, 17, and 25 plus 8 gives us our upper bound, 33. Now that's our interval. We say that that has a 99% confidence, right? That's the complement of alpha. Similarly, we could write this as an inequality where 17 is the lower bound, and that's less than or less than the population mean mu, less than 33. Now notice that we knew to use mu because we were given a sample statistic of x bar equals 25. X bar is the sample mean, so we're making a claim about the population mean, mu. Now, we're also supposed to say this in words, so we're going to start by saying that there's a 99% chance, we could say probability there, but chance is just as good, that the that this interval captures the true population mean. So that interval from 17 to 33 actually contains the population mean. Your intuition will tell you that if you want to have more confidence, if you want a larger confidence level, then that confidence interval is going to have to be larger than if you want a smaller confidence level. So for example, a 99% confidence level will give us a confidence interval that's much bigger than a 90% confidence level. At a 90% confidence level, we only have to be 90% sure that our interval captures the true population parameter. So there's a trade-off between the width, how wide that interval is, and the confidence level. So you can be very confident about your answer, but not be very precise. So in other words, if I want to be precise, I can have a smaller margin of error. If I want a precise answer, I'm not going to be very confident about my answer. That 90% confidence interval is smaller than the 99% confidence interval. So looking at this example, we can see that the 95% confidence interval lines up pretty well with those numbers on the number line there. So we could say that there is a 95% chance that the true population mean is between 4.8 and 5.2. Samples have the opposite effect on the confidence interval. That's largely because the standard deviation of the sample means is the population standard deviation divided by the square root of n. In other words, the standard deviation gets smaller as n gets bigger. So notice that that smallest interval, when n equals 1,000, is also true for the largest sample size. Comparing that to n equals 100, it's much smaller, much more precise, and that's because the sample is so much larger. Larger samples are closer to the true population, so their point estimate is already pretty close to the true value. So suppose that you compute a confidence interval with a sample size of 25. What will happen to that confidence interval if the sample size increases to 50? So here we're starting with a smaller sample size and we're increasing it to a larger one. And as we do that, the standard deviation of the sample means gets smaller, and so we can expect that that confidence interval will collapse, will contract around the point estimate, the center of that interval.